Hello! We are ready to start Unit 4. Hopefully by now, or I know by now, I will have shared the Unit 4 doc, which is the KUDs for this unit. The major topic of this unit is the introduction of integration. So integration starts with the antiderivative. Well, the antiderivative. What is the antiderivative, you might ask? Let's find out. So if you took the derivative and you ended up with, oh, there it was, a little slow on the uptake, and you ended up with y prime equals 4x cubed, what'd you start with? What was the actual function that you took the derivative of to end up getting that answer? Hopefully, you might be thinking x to the fourth. So we're working our way backwards, and so like, what's the derivative of x to the fourth? 4x cubed. If we took the derivative and we ended up with y prime equals the cosine of x, what did we start with? Y equals the sine of x, because the derivative of sine is cosine. If we took a derivative and we ended up with y prime equals 3x squared minus 5x, what did we start with? What did we take the derivative of to make that happen? That's right. X cubed is the first part, minus 5x squared over 2. Okay, check that. X cubed. 3's are really awful lately. All right, 3 there. 3x squared minus 5x. You with me? If we ended up, after we took the derivative, with 1 over x squared, what did we start up with? You might be thinking negative 1 over x, or at least I hope that's what you're thinking. It's negative 1 over x. So remember, 1 over x is x to the negative 1. Bring that in the front. That would become positive. X to the negative 2 would be that. Okay? So what we're doing is we're working our way backwards from the derivative back to the other way. See why it's called the antiderivative? Because it's the anti of the derivative. All right, so now we're going to go forward. We're going to find the derivative of x cubed plus 7. Derivative of x cubed plus 7 is 3x squared. The derivative of x cubed minus 4 is 3x squared. The derivative of x cubed minus 11, 3x squared. The derivative of x cubed plus 5, 3x squared. Derivative of x cubed plus pi, 3x squared. Okay? So, there's a pattern there, I think. Maybe. Hopefully you saw the pattern. The question that the pattern begs is, those are all the derivatives of all those things. What's the antiderivative of y prime equals 3x squared? Work backwards. Again, go back to the way I asked it on the last slide. If we took a derivative and we ended up with y prime equals 3x squared, what did we start with? Could have started with that, or that, or that, or that, or that, or that, or any of those things, right? So what we do to note that we could have started with any constant, we would say that y, the antiderivative, was equal to x cubed plus some constant. Okay, so when we're taking an antiderivative, working our way backwards, we always include some sort of a constant in the answer. Okay, so I should go back and fix these with a plus c, a plus c, a plus c, plus c, all the way through. Anytime we take an antiderivative, we need to have that constant because there could be any number trailing along at the back, as this shows, even pi, and we end up with the same derivative. So, all right. So, notation-wise, we're familiar with the derivative, dy dx equals the, well, we're not familiar with that notation, but we're going to just say that the derivative, we're going to call that lowercase f of x, okay? Differential form, remember that? Lowercase f of x is not as good as theirs, okay? So, that's differential form. What we're going to do is we're going to take the antiderivative, and we have a notation for antiderivative. It's this. Looks kind of like an s, but it's a little elongated. It's the integration sign. If we take the antiderivative of dy, we get y. If we take the antiderivative of lowercase f of x, notation-wise, we get uppercase f of x plus c. Okay? Don't forget plus c. Okay? Don't forget to add the c at the end. So the difference is, this is the derivative, this is the actual function as we go through. So this is what's called an indefinite integral. The process that we just did, an antiderivative and an indefinite integral, they are the same thing. That's what I just wrote on that previous slide. Okay. The f of x right here, that's called the integrand. That's the thing that we are taking the integral of, or the antiderivative of. The variable of integration, that's this dx part. Okay, it says that we are integrating the x variable. Uppercase f of x, that's the antiderivative. And the constant of integration is plus c. Okay, so don't forget plus c. Okay? Indefinite integral. That's just the antiderivative. So it turns out that if I take the antiderivative of a derivative, I get the function back at a plus c. If I take the derivative of an antiderivative, I get the function back. Okay, so if I take the derivative of the antiderivative of some function, I get the thing back as I work. And you might be able to see that. It's such a small, that's not what I wanted. I wanted pointer, 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 pointer. Okay, it turns out that differentiation and integration are inverse operations. Okay, they do the opposite of each other. So if I take a derivative and then I take the antiderivative, we'll just go back where we started. Or if I take the derivative of an antiderivative, I go back where I started. They're inverse operations. Okay, you know other inverse operations you've learned through the years. Okay, and there are rules for all these things, and you have them on your little card that you've had for a long time. So you know, if I look through the derivative of the derivative of a constant is 0. The antiderivative of 0 is a constant. The derivative of a constant times x is a constant. The antiderivative of a constant is the constant times x plus the constant. So it works all the way through. We've got pluses and minuses. We've got our power rule. We've got the power rule in reverse. Okay, power rule in reverse, add 1 to the exponent, divide by the new exponent. All my sines and cosines, they have antiderivatives. Okay, so all those things that we knew in the front end, we can work our way backwards on the back end. Okay, we're just doing everything backwards. We're antiderivating. Okay, well, Dora still applies. With Dora, we must rewrite. We must now integrate, and then we can simplify. Okay, so what we are limited with our integration is it's got to fit one of the patterns that we know. We're looking. It's all about making it look like something that we have a rule for. So it's a little more restrictive than the derivatives, because derivatives we can punch a bunch of things together. We had product rules and quotient rules, so we could do combined things. With integration, it pretty much just got to fit one of the rules that we have, and I think there are about 19. They're not all right here. They're on page 250 in your book. These ones, and they're also on your card. There's a few more that we have that aren't here. All right, so rewrite, integrate, simplify. So the rewrite, remember, hopefully, is that this becomes x to the 1/3 dx. When we take the antiderivative, so we do the opposite thing. We used to multiply by the that's the word, the exponent, multiply by the exponent and add 1 to it. Oh, wait, try that again. We used to multiply by the exponent and subtract 1 from it. In this case, we're going to add 1 to the exponent and divide by our new exponent. So this becomes x to the 4/3, because 1/3 plus 1, divided by 4/3 plus c. Like dividing by 4/3 is the same as multiplying by 3/4, so we typically will write this as 3/4 x to the 4/3 plus c. Okay, that's what my function is. So if this is the antiderivative, then I'd write it as this particular thing right here. I don't know if I left myself enough room, but you know what I can do? Watch this. Just move it down a little bit. And voila, I've got plenty of room. All right, so we rewrite this thing. We know how to deal with when we have things in the bottom. This becomes the antiderivative of x to the -6 dx. The rule says, and I'm showing you which rule I'm talking about. I'm talking about, where is it? This rule right here. My power rule. Add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent. Make that your new best friend. Okay? Sorry to all your old best friends, but you've got a new best friend now. Add 1 to the exponent. Add 1 to -6. I think I'm at -5. Divide by the new exponent. I'm at -5. Don't forget the constant. We need to put the constant in as soon as we get there. As soon as we take an antiderivative, we write the constant. We want it to be a constant of integration, not a constant of desperation. That we just go, oh, I forgot the constant. I must put it in now. Okay, so then we don't leave this way. This way. We rewrote. We integrated. Now we must simplify, and we never leave negative exponents. Never, never, never. So this becomes 1 over, actually -1 over 5x to the +5 plus c, and we are done. Okay? So, and we usually will write this like y equals or something like that. We've taken an antiderivative, and that's how it works, okay? Antiderivatives, they are our friends. Those are some things. They're not just, we're not opposed to them. Integrals are good, okay? That's what we're talking about. I will leave you with Dora. Rewrite, integrate, simplify. She's got it all going on here. What do I need to do? I need to go full screen and bid you adieu. Thanks for watching. Hope you pick something up. We'll work with this for the next couple of days. Then